So in this video, we're going to see a problem from exercise 9.2, and this is problem number 4. So let's read what the problem is. In figure 9.16, so this is figure 9.16, P is a point in the interior of a parallelogram ABCD. Okay, so let's use a highlighter. This is a parallelogram ABCD. Okay, and P is a random point in the interior of a parallelogram, inside the parallelogram. That's it. That's the piece of information given to us. Show that area of APB. So I'm going to use the highlighter again. So area of APB. So this triangle, okay, plus area of PCD. So PCD, this triangle. So the area of these two triangles is equal to half the area of ABCD. So ABCD is the whole parallelogram. So that is the first thing that we have to prove. Now let's see how that can be done. First, let me erase this highlighted things. Yes, okay. Now, there's an important hint that is given to us. So let's highlight this hint. Through P, draw a line parallel to AB. So let's use this hint and try to solve this problem. Okay. So first thing I want to do is through this point P, draw a line parallel to AB. So this is the line, okay, which is through P and it's parallel to AB. So this is AB, okay, and this is parallel to AB, and this is also parallel to CD. Okay, now let's focus on. I'm going to use a highlighter. Let's okay, let's first give some names. So let's call this point as X. Okay, this point is X, and let's call this point as Y, and this point is the P. Okay, now focus on the parallelogram A, B, Y, X. Okay, focus on this quadrilateral. So first observation is it's a parallelogram. So I'm going to make that point 1 first. Quadrilateral A, B, Y, X is a parallelogram. Okay, it's a parallelogram. Why? Because AB is parallel to XY. That is the way we have constructed the line. And this by is already parallel to ax because it's a part of this whole bigger parallelogram. So if the opposite sides of a quadrilateral are parallel to each other, then the whole quadrilateral will be a parallelogram. Okay, so this highlighted quadrilateral is a parallelogram. Okay, now if you consider this triangle, APB, okay, so this triangle ABP and this quadrilateral, okay, ABYX, both of them are between these two parallel lines AB and XY. Okay, and both of them have the same base AB. Okay, so this is an important point. Point number 2. So both triangle ABP and parallelogram ABYX have, what do they have? A, common base. So common base AB, and B, located, both of them are located between two parallel lines. Okay, so we all know that there is this theorem which we have proved in the previous video, that if the triangle and the parallelogram have a common base and both of them are between two parallel lines, same two parallel lines, then, okay, I'm going to zoom this, okay, then the area of area of triangle ABP is equal to half the area of parallelogram, which is ABYX. Okay, this is a theorem which we have proven in the previous videos, so you can go and check them out. Okay, so I'm going to quickly revisit this point. both triangle ABP, so this is the triangle ABP, and the parallelogram ABYX. So ABYX, they have a common base and they both lie on the between the two same parallel lines. If this is the scenario, then the area of the triangle is half the area of a parallelogram. Okay, so this is the thing that we will be using henceforth. So first of all, I'm going to erase this highlighted part. Okay, and I'm going to mark this. Okay, this is an important equation. I'm going to mark this as equation number 1, which we are going to need in the future. Now once again, using the same logic, we are going to prove that the area of triangle DPC, okay, is half the area of quadrilateral XYCD. Okay, I'm not going to repeat the entire proof or the entire process. The logic and all the steps are same. I'm just going to read them out. So again, this, okay, so this XYCD is a parallelogram. That is the first thing we have to prove. Why is it a parallelogram? Because XY is parallel to DC by construction, and XD is parallel to YC because they are the opposite sides of this bigger parallelogram. So first step will be to prove that this is a parallelogram. Then in second step, we prove that this parallelogram and this triangle, they have a common base BC and they both lie between the same parallel lines. Okay, and by that logic, we can confidently say thus. I'll put that as point number 3. So okay, so I'll just say similarly, area of triangle DPC is equal to half the area of parallelogram XYCD. Okay, and now this will be my equation number 2. Okay, and now step number 4, which is a very simple step. I'm going to add equations 1 plus 2. Okay, so what is that going to be? So let's quickly see what do we want here. So I'm going to zoom out now. So focus on these things. Yeah, we want area of APB plus area of PCD. Okay, so when we add these two equations, that is what we get on the left hand side. So okay, let's zoom in here. So I'm going to add both the equations. I'm going to get area of triangle APB plus area of triangle DPC is equal to half of, okay, so half is common and it's going to be area of parallelogram ABYX plus area of parallelogram XYCD. Okay, and now let's focus on the original diagram. I'm going to zoom out. Okay, so look at this ABYX. So this is ABYX plus XYCD. So XYCD. So these are the two small parallelograms. If you add these two small parallelograms, you get the area of the whole parallelogram ABCD. Okay, so that is what we are going to substitute in the right hand side of the equation. So it will be half of area of the bigger parallelogram ABCD. Okay, and thus we have proven that area of these summation of area of ABP plus DBC is half the area of the whole parallelogram. This is what was asked to be proven in first point. So I'm going to just mark it as done. Now let's remove this highlighted things. Okay, now let's focus on what is the second thing. The second thing is area of APD. So APD plus area of PBC. So area of PBC is equal to area of APB plus BCD. Okay, so again the second point is exactly similar to the first point. what we have to prove in the second thing is area of APD plus area of BBC is also equal to half the area of ABCD. Okay. Now the way we are going to do this is, let us zoom in and let us erase this line now. Okay. So yes, let's erase this line. Okay. So I'm going to construct another line through point P, but this time I'm going to construct a line parallel to AD and parallel to BC. In the first thing, we constructed a line parallel, like a horizontal line which was parallel to AB. Now let's consider construct a vertical line passing through point P and parallel to AD. So let's do that. Okay, so this is the construction. Construct a line passing through point P and which is parallel to AD. So it doesn't really look parallel to AD. So let me make another attempt. Okay. Okay, this is a bit better. So this line is passing through point P and parallel to AD. Now once again, let's name these points as X. Okay, name these points as X and name this point as Y. Okay, now once again, I'm okay, let's do one thing. Let's should we erase this? Yeah, let's erase this. But the logic or the approach and the steps are exactly the same. Okay, let's zoom out. Okay, so step number one. So quadrilateral AXYD. So I'm going to highlight it. AXYD. This quadrilateral, okay, is a parallelogram. So that is the first statement that we are going to make, that it's a parallelogram. Why is it a parallelogram? Because this side is parallel to this side, that is given, and this side is parallel to this line as per the construction. Okay, that's the first point. Now, second point is in triangle APD. So let's highlight this triangle. This is a triangle APD. Okay, and sorry. So in this triangle and in our new parallelogram AXYD, in both these figures we have two things in common. Okay, first thing is common base. So which is that common base? Common base AD. And second thing is both lie between same two parallel lines. Okay, and because of this property and because of this design, we can say point number 3. I'll say hence we can say, what can we say? That area of triangle APD is equal to half the area of parallelogram, which is a parallelogram. This is a parallelogram. Okay, this is a parallelogram which we mentioned in the first point. It's half the area of parallelogram so AXYD. Okay, that is the first point. Now once again we will remove these highlighted things. Okay, and now we will switch our focus on the other half. What is the other half? It is this parallel. Okay, it is this parallelogram XBCY. Okay, this parallelogram, and then we have this triangle BPC, this triangle. Okay, similarly, same as the previous proof, we have BC as the common base for both the triangle and the parallelogram, and both of them lie between these two parallel lines. So once again we can say, I'm going to zoom out. So point number 4. Okay. Similarly, area of triangle BPC is equal to half the area of parallelogram XBCY. Okay. So let's remove the highlighted part. Yes. Okay. Now we are going to add both of these equations. So APD plus BPC, this is APD plus BPC is equal to half. Okay, and we're going to add these two parallelograms. Okay, so let's do that. So adding both. Okay, we get area of triangle APD plus area of triangle BPC is equal to half. And now I'm going to make a jump here and not mention each and every step. So this parallelogram plus this parallelogram, so it is this parallelogram plus this parallelogram. So summation of both the parallelograms is equal to the whole big parallelogram ABCD. So that is equal to half the area of parallelogram ABCD, the original parallelogram. Okay. So thus, yes, and thus we prove the second point. So in second point, this APD plus BPC. So APD plus BPC is equal to ABP plus PCD. So ABP plus PCD, which is also equal to half the BCD, half of ABCD. So thus we also prove point number 2.